welcome to Quick Science. The periodic table could be considered the Rosetta Stone of chemistry. Each element is grouped and placed in specific rows and columns in order for chemists to crack the mysteries of chemistry. But the question is, how are we able to structure the periodic table? The answer is electron configuration, in which the periodic table is derived from. Electron configuration is the arrangement of electrons in the orbitals of an atom or molecule. In this video, I will show you the basics of electron configuration and its relation to photoelectron spectroscopy. A stable electron configuration of an atom is the ground state in which the electrons are in the lowest possible energy states. Take, for example, that there are no restrictions on the possible values for the quantum number of electrons. If that happened, every electron would crowd the 1s orbital since it has the lowest energy, sort of looking like a weird Coachella concert. However, the Pauli exclusion principle tells us that there can be at most 2 electrons in any single orbital. This explains how orbitals are filled in order of increasing energy, with no more than 2 electrons per orbital. In order to represent the electron configuration of an atom, an orbital diagram illustrates how many electrons are in each orbital. In an orbital diagram, each orbital is represented by a box. An electron is shown as a half arrow either pointing up or down. An arrow pointing up shows an electron with a positive spin magnetic quantum number, and an arrow pointing down has the opposite spin. Opposite electrons are said to be paired while they occupy the same orbital. They can also be unpaired electrons in an orbital. Here's an example. Lithium has 3 electrons. Recall from the past that the number of electrons in a neutral atom is equal to its atomic number. So its orbital diagram would be 1s2, 2s1. Lithium has a complete first shell, but has an unpaired electron in the second shell. However, due to the change in principal quantum number, it represents a large jump in energy and in the average distance of the electron from the nucleus. Here's another example. Carbon. This atom brings a new idea to the table. Carbon has 6 electrons, so it has already filled up the 1s and 2s orbital shells and has moved to 2p. The 5th electron already occupies one 2p orbital, but does the last electron pair with the 5th electron, or does it occupy a new 2p orbital shell? This is where the Hund's rule comes into play. The Hund's rule states for the degenerate orbitals, the lowest energy attained when the number of electrons with the same spin is maximized. This means that electrons will occupy orbitals singly to the maximum extent possible, and that these single electrons in a given subshell will all have the same spin magnetic quantum number. So in order for the carbon to achieve its lowest energy, the 2p electrons, or the 2 arrows, will have the same spin or be placed in separate boxes and have 2 unpaired electrons. When talking about electron configuration, the concept of the distance of electrons between the nucleus is very important. A subshell number shows that there is a large jump in energy between the 2 different subshells. To have a better understanding of energy jumps, take a look at the Bohr's model. The first energy level is the closest to the nucleus but has the lowest energy. In order for the jump to happen, a large amount of energy is absorbed to move to the second level of energy, and so forth. Since this happens, you can think of the first energy level as 1s orbital, since it has the lowest energy and is the closest orbital to the nucleus. Since we are talking about distances of electrons in the nucleus, it's about time to include photoelectron spectroscopy. Photoelectron spectroscopy, or PES, is an experimental method used to determine the electronic structure of atoms and molecules. The experimental method is done with the photoelectron spectrometer. Photoelectron spectrometers ionize samples by bombarding them with high-energy radiation, such as UV or X-rays, and detecting the number and kinetic energy of ejected electrons. By analyzing the kinetic energy of ejected electrons, features about the electronic structure of the sample material could be determined. Since there are 2 methods of electron spectroscopy, I'll be going over X-ray PES. Since X-rays are higher in frequency and energy than UV rays, shining them on a sample can provide enough energy to eject core electrons. Core electrons are inner-shell electrons that are closer to the nucleus, such as the 1s orbital, and thus require more energy to acquire compared to valence electrons. Once electrons are ejected from the sample, a detector is able to calculate the kinetic energies of the electrons, as well as the relative number of electrons with that kinetic energy. We can use this information to calculate the minimum energy required to remove electrons from different subshells within an atom. This is called the binding energy of the electron, and the binding energies depend on the chemical structure and elemental composition of a sample. We're able to simplify the experiment with the PES spectrum, a graph of relative electron count versus electron binding energy. The peaks in PES spectra correspond to the electrons in different subshells of the atom. The peaks with the lowest binding energy correspond to valence electrons, while the peaks with the highest binding energy correspond to the inner shell or core electrons. You can even determine the electron configuration by looking at the PES graph. Since the electron configuration of lithium is 1s2, 2s1, its PES graph would look like this. There are two peaks in the graph, meaning that two subshells have electrons, one peak having 2 electrons and the other only having 1, so in total there are 3 electrons. By looking at the periodic table, lithium has 3 electrons, so the graph is showing this element. The configuration is determined by the peaks as well. The peak with the highest energy is the closest to the nucleus, so it is a 1s orbital, and has a filled subshell, while the last peak has only 1, with the lowest binding energy needed to eject, meaning it is a 2s orbital. Since we have gone both over electron configuration and photoelectron spectroscopy, it's now time to go over the problems of these two chemistry concepts. First problem is, what is the electron configuration of copper? It would be best if you pause this video now. Okay, so the answer is not what you would expect. There are 2 elements accepted from the Hund's rule, copper and cobalt. The electron of copper is not 1s2, 4s2, 3d9. The electron configuration is actually 1s2, 4s1, 3d10. The reason for the unpaired electron is the 4s orbital is that its completely filled sublevel is more stable than a partially filled sublevel. The next problem is the PES graph. Interpret the graph, hint, what is the electron configuration, and figure out the element represented in the graph. Now it would be time to pause the video. This graph shows the element aluminum, since it has 13 electrons. And the configuration would be 1s2, 2s2, 2b6, 3s2, and 3p1. That would be the end of the video. Thanks for watching.